Okay, probably it's now time to start. It's already 8:30 by Moscow time. So, hello again. My name is Andrei Raigorovsky. I am professor of Moscow Institute of Physics and Technology, and my project is devoted to some graph theory. I assume that everyone here knows what is a graph, but probably I am too enthusiastic, no? Too optimistic. Everyone knows what's a graph on n vertices, for example. How many graphs on n vertices do we have? It's a question. You may answer, for example, not by using your voice, but by using chat. So you may write it down in the chat. How many graphs on n vertices, how many different graphs on n vertices can be drawn? In fact, it's a difficult question since we have to make it more precise. What do we mean by a graph? Here, I assume that a graph is a simple graph. So it has only simple edges, not oriented ones, no loops, no multiple edges. So if you have n vertices numbered, for example, by first natural numbers, say 1, 2, 3, 4, and so on, n, then let's first decide how many edges can be drawn on this set of vertices. Could you write it down in the chat or pronounce it in words? What's the number of edges in a complete graph on n vertices? Complete graph on n vertices. All the edges are drawn. Or I have to define what's a graph. Do you hear me? Do you understand my question? I don't see any reaction. Aha. Okay. And choose 2. Yes, it's a number of edges of a complete graph on n vertices. It's right, of course, and choose 2, which is of course equal to n times n minus 1 over 2. This is the same. And so how many graphs, how many different simple graphs on n vertices do we have? If the number of edges in a complete graph on n vertices is written down here in the chat, and choose 2. How many graphs? Different graphs. Not non-isomorphic, but different in the sense of different edges, numbered edges. I give this question in order to understand whether you understand me. Maybe there were some other replies. And choose 2. Yes, I see it. And that's all. But of course, if you have a complete graph on n vertices, and it has n choose 2 different edges, then every edge of this graph can be drawn and can be not drawn. So 2 different variants for every edge. How many graphs do we have? 2 to the power n choose 2. 2 to the power n choose 2. I don't want to work with some writing tools. I just want to do it by words. So this number n choose 2 must be taken like a power of 2. 2 to the power n choose 2 is the number of all possible graphs on n vertices in case we understand that a graph is simple. So my project is devoted to a question which goes back to Turan. It's a very famous Hungarian mathematician, Paul Turan, who proved, roughly speaking, the following result. You have an arbitrary graph on n vertices, from this number of 2 to the power n choose 2 graphs, and you assume that the independence number of this graph, I will explain you what is the independence number of a graph, you assume that independence number of this graph is less than or equal to some value, say some alpha. In this case, it's possible to bound from below the number of edges in this graph. Necessarily, the number of edges in this graph is big enough. What is the independence number of a graph? It's the maximum number of vertices of the graph, which are pairwise disconnected. There is no edge inside this set of vertices. For example, if you take a simple cycle like a polygon on n vertices, a simple cycle on n vertices, then its independence number is entire part of n over 2, since you may take vertices which are not joined by an edge. One vertex, then you don't take a vertex which is joined by an edge with this one, and then you take the second vertex, and so on. This is the independence number of a simple cycle. So what is, in fact, what is actually the independence number? It's the maximum number of vertices which form like a hole in a graph. There are no edges inside it. So if for a graph on n vertices, alpha of G, which is the usual notation for the independence number, is small enough, if the independence number is small enough, then the number of edges must be big enough, large enough. It's intuitively, it's very easy to understand it. If you have very small holes, then in every large enough set of vertices, you have an edge. So the total number of edges in the graph must be big, must be large. And this is a kind of Turan's result. In our project, you will have all such problems just in the beginning, which show how to prove a classical Turan theorem and to prove that it is not improvable. It's impossible to prove a better bound from below for the number of edges in the graph in which the independence number is bounded from above somehow. So, but this is very simple, and a lot of us know it just from the beginning. Maybe it's not necessary even to get such a project in order to know Turan's theorem. But the main goal of this project is to study the same questions, not for all possible 2 to the power n choose 2 graphs on n vertices, not for all possible, but for some specific, very interesting subclasses of the total class of different graphs. For example, we study in this project the so-called distance graphs. What do I mean by a distance graph? In the simplest case, we consider a plane, regular plane, an ordinary plane, Euclidean plane, and by a distance graph on the plane, we just mean such a graph whose set of vertices is a set of points on this plane and whose set of edges consists of all possible pairs of points which are at the distance 1 apart. So you put some points on the plane, you fix the distance 1, and then you choose all possible pairs of points which are at the distance 1 apart. And this constitutes a graph, which is called distance graph on the plane. For example, if no 2 points on the plane have distance 1 apart, then you get just an independent set without any edges. But for example, it's impossible to realize a complete graph on 4 vertices on the plane as a distance graph, since there exists no regular tetrahedra on the plane. It's only possible to draw on the plane a regular triangle with all the edges equal to 1. But if you want to find 4 vertices, which are pairwise connected by a segment of distance length 1, then it's impossible, of course, to do it on the plane, on Euclidean plane. So the class of all possible distance graphs on n vertices is much smaller than the class of all possible graphs on n vertices. Its cardinality is much smaller than 2 to the power n choose 2. It's something. I don't want to go into the details right now. So if you consider a distance graph on a plane, then of course a Turan bound may be also proved for it, but it's of a different form. For an arbitrary graph, the lower bound for the number of edges in case the independence number is bounded from above and the number of vertices given is of one form. And for a distance graph, it's of another form. And in the project, we will also see how to prove such bounds and how to try to prove that it's impossible to improve them. But even in the class of distance graphs, it's possible to consider very interesting subclasses of graphs. For example, some combinatorial classes of graphs. Maybe some of you, I don't know, of course, but maybe some of you have heard sometime the so-called Kinesthetic graph. It's a very famous object of classical combinatorics and graph theory, which was studied starting from 50s of 20th century. And in the 70s, the chromatic number of this graph was calculated using some topology. But of course, we don't want to go into such details, and we don't suppose to use profound topology here in this project. However, it's possible to study such graphs like Kinesthetic graphs. And just roughly speaking, everything is depicted in the project, everything is accurately defined there. But just to make it here in this presentation, what is a Kinesthetic graph? You have a set of n natural numbers, for example, 1, 2, 3, and so on, n. But now they don't form necessarily the set of vertices. This is just some underlying set. And you fix a value, say r. And you consider all possible r element subsets of this set of n first natural numbers. So you have first natural numbers, n first natural numbers, and you consider all possible r element subsets of this set. So the number of such r element subsets is, of course, n choose r. And this is the number of vertices in the graph of Kinesthetic. So Kinesthetic was a mathematician who invented this graph, and two sets of cardinality r, two vertices of this graph, are joined by an edge if they do not intersect at all. So if r is greater than n over 2, then of course this is just an independent set. No edges can be drawn since every two r element subsets intersect. But if r is smaller than or equal to n over 2, then this is an interesting graph, and it's very difficult to calculate different values. For example, it's even very difficult to understand what is the independence number of this graph, but it's possible to understand it, and we will do it in our project. So why this graph is a distance graph, it's also explained in the project, but such a graph is also distance one. So it's a very interesting subject to study different classes of graphs and trying to understand how the number of vertices, the independence number of this graph, and a lower bound for the number of edges are connected. And this is the aim of our project, I would say. So if you have some questions about what I have said, maybe you didn't understand some definitions, or maybe you did not hear the main idea of the project, please ask me in the chat or by voice, as you wish. But everything is defined clearly in the papers, which were, I think, diffused among you. So, of course, I would be happy if you join our project, and it's possible. What is very important to say, it's possible to prove absolutely new results here. So it's not only possible to understand how it works, like high school students do usually, but it's also possible to try to prove absolutely new results in this area. Since, how to say, the threshold for entering to this science is not so high. It's very easy to understand classical results, to reprove them, and after it, to try to prove absolutely new results concerning some subclasses of graphs, distance graphs or Kinesthetic graphs, or some generalizations and so on. So I invite you to try to make new results here, and even probably publish papers concerning them. Such a branch of combinatorics and graph theory is here. Okay, so I don't hear any question. Probably I was not too, how to say it, understandable, but maybe you understood everything. So let's try, let's do it. No questions. Okay. Let's see who will join us. Thank you for your attention. Please look at the problems and try to choose. See you.